Okay, so as we've seen a few times, the point of a Taylor series is that we're taking some function that's typically not a polynomial, and we're rewriting it as an infinitely long sum of polynomials. And we've seen a few examples of how to do this. We've sort of seen why there's a certain formula that relies on calculating derivatives. It's this formula. And so if we've got some function and we can take a whole bunch of derivatives, we should be able to write out its Taylor series. That said, for a lot of functions, finding this pattern in what the derivatives look like isn't always quite as straightforward. We've typically been working with things like trig functions that get cyclic, or e to the x, which just sort of always stays the same. We want to be able to deal with functions that don't necessarily follow as obvious a pattern. So just like with, or in a similar vein to our derivatives and our integrals, where we took different known entities and put them together in some way. Things like product and chain rule and their integral equivalents. We're going to learn a couple tricks as to how to put together known entities of, or known series, known Taylor series, to be able to figure out a Taylor series for a function that might not, a function whose derivatives might not follow such an obvious pattern as e to the x. Okay, and so we're going to start off with this function, 1 plus x cubed. And I'm saying, all right, we want to find the Taylor series for this, which may raise an alarm of like, wait, the whole point of Taylor series is that we're going to rewrite something that's not a polynomial as polynomials. This function is already a polynomial. And that's absolutely right. It doesn't mean we can't do this. It doesn't mean this is kind of a silly thing to do for this particular example. But the point of this is that we're going to be establishing a pattern that's going to let us use a more general rule. Okay. So when I say I want to find the Taylor series for this, in order to find a Taylor series, we need this information. We need the value of the function, the derivative, the second derivative, third derivative, etc. I probably should have also specified here that I want the Taylor series centered at x equals 0. Okay, so in order to find this, we need to know what the derivative of this function is. Well, the derivative, we can use the power rule. We can bring down the 3, and it's 1 plus x squared times the derivative of the inside. That just ends up being 1, so we can sort of leave that part alone. The second derivative, we can apply the same rule again. We get 3 times 2, 1 plus x to the 1 times 1. The third derivative, this is just going to be 3 times 2, and then we pull down a 1. The exponent here drops to 0, so that just entire thing becomes a 1. 3 times 2 times 1. Okay, so what we don't actually necessarily need the derivatives. We need the derivatives evaluated at the point in question. So we're going to plug 0 into each of these derivatives, and we're going to see that, well, first off, our f of 0 is 1, but our f prime of 0 is 3. Our f double prime of 0, I'm going to leave this as 3 times 2. We're trying to spot a pattern here. And our f triple prime is 3 times 2 times 1. Okay, so we can take these pieces and calculate the Taylor series with them. Therefore, our function f of x, this thing up here, is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime, I dropped a prime over here, f triple prime of 0, oops, f triple prime of 0, which is 3 times 2 times 1 over 3 factorial. Plus, let's also include the fourth derivative. Well, the fourth derivative of this, the fourth derivative of 6 is just 0, so plus 0. And we're going to get a bunch of more plus zeros because more and more derivatives of 0 is still just going to be 0. All right. And I want to point out that when you multiply this out, we get 1 plus 3x plus, well, this 2 and this 2 cancel, so 3x squared. The top and bottom here are both 3 factorial, so we get a plus x cubed. Right? So this is the Taylor series expansion of the function 1 plus x cubed, which this is where it seems like, all right, why on earth would we ever do this? The answer is no, we just wouldn't ever really, because this is the same thing as if we multiplied this out. Right? The reason I wanted to go through this is I wanted to point out a couple of things that happen. One is that when we get past 3, we're taking higher derivatives, all of our terms are just going to end up being 0. Right? Another thing I wanted to point out was this pattern that we're getting. We're going to get whatever our exponent is here, we're going to be multiplying by that exponent, and that exponent times 1 minus that exponent times 1 minus that times 1 times 2 minus that, etc. So the reason we're doing this example is because this generalizes. Rather than talking about the Taylor series for 1 plus x cubed, we're going to change it to the Taylor series of 1 plus x to the p. We're going to make that exponent some generic term. And I want to point out that this pattern that I was talking about, where we've got, with our 3 example, it was 3, and then the numerator here was 3 times 2, numerator was 3 times 2 times 1, and in this case, once we got further, we ended up with some 0 terms. Okay, so you can walk through the details of this in the book. They go through the same derivation, but with a p instead. What I wanted to point out, or the reason we care about this, is not for p values that are positive integers. If we plugged in a 4 here and did all those calculations, we would get the same thing as if we just took 1 plus x to the 4th and multiplied that out. Right? The reason this is useful is that this works for p values that aren't necessarily an integer exponent. They work for negative numbers, they work for fractions. Right? So for example, if I wanted to find the Taylor series expansion for the square roots of 1 plus x, or maybe for 1 over 1 plus x, we can use this idea with various values of p, and we can keep applying these rules. So this is p equals -1. We can still take 1/2 minus 1, that's just -1/2. And for these values, our series is going to be infinitely long. We're never going to get this collapsing down to 0 case. Okay, so when we move on to section 10.3, we're going to learn more ways of combining things, of combining series. But this type of thing is actually going to give us a lot of building blocks. You might be thinking 1 plus x is a pretty limiting thing to put on the inside. We'll have ways of changing what this x is moving forward.